Today we will look at what is binary search. Generally whenever we are given an array and we need to find the index of a particular element in the array, and if the array is not sorted, what we do is like we do a linear search. And what linear search basically does is like it traverses through each element in the array. Like in this particular example, it will be 1, 2, 5, 6, 3, 4. And so the index of the element 1 would be 0, index of element 5 would be 2, because we start from 0 and then 1, 2, 3, 4, 5, so on. That's how the linear search is done. And as you can see, like this is the code for linear search. If we want to do linear search on a particular input list and we are given an element, we would simply iterate through that list and see if the current element is equals to the element. If yes, then we would simply return the index, and if that is not the case, we return -1. And here I've written some tests for it. So this is the input list, and we simply iterate through the list, and then we do a linear search, like apply linear search for each one of them, like and just see if the resulting index is really equals to the index. So this is how we are testing it, and there is one edge case test here as well, like search for an element which is not present in the list. So that gives us -1. But now what is binary search basically? So right now the given element was not sorted, but binary search works on sorted array or sorted list. So we will come to the time complexity next. So how binary search works is like if you are given a sorted array like 1, 3, 4, 6, 9, 10 in this way. So these are sorted in ascending order. And so what we do is like basically we start at the middle element. So for this middle element can be 4 or 6, but so generally we take the first one, like if it is even. So let's say we have 6 elements present over here. So we will take third element. We could have also taken 4. Both of them are in middle, but for this algo we will take 4 as the middle, and then so if we consider 4, and then we will see if the given element is really equals to 4 or not. If it is equal, well and good, we will simply return the index of 4. If not, then now we can make a choice here, like either consider the right subarray or consider the left subarray. And how would we do that? We would see like the given element, is it lesser than 4? If it is lesser than 4, then we would just consider left subarray. But if the given element is greater than 4, then anyways we know like elements which are left to 4 are anyways smaller than 4. So we don't even need to consider them. We will only consider the right ones for the element which is greater than 4. And we will follow the same algorithm iteratively over and over till either we don't have any element to, like any subarray to consider, or we find that element. So that's what this binary search is about, and we will see how it optimizes code of binary search. So in binary search, again we are given an input list and an element. Input list is sorted, and the start index of the, we will set the start index as 0 and end index as the last index of this particular input list. So length of input list -1, and the middle element, right now we don't have any middle element, so the middle element's index is set as none. And here this particular condition is really important, like while start index is less than equals to end index. And why is that so? Because if we are given a valid list, it will always be the case that the start index is less than or equals to end index. And if that is not the case, we are not considering the right list. So for example, if the input list was like had 0 element, like no element at all, in that case start index would be 0, but the end index would be, length of input list would be 0 and then -1. So it would be 0 and -1, which is not a valid list. And the same will hold true when we are like considering the different subarray or sublists down the line. So this condition is really important, and once we apply this condition, now we can change the middle element and apply the same algorithm that we talked about. So we will set middle here, like not initialize, but set the middle here, and it will be start index plus end index minus the start index divided by 2. So basically this will tell us like how much should we add to the start index to get the middle element, like the middle index. And this is just to calculate the middle index. And now we check if the middle element is equals to element. If that is the case, we just return the middle index, this mid. But if that is not the case, now we have two conditions. Either the middle element is less than the element, like the element that we are searching for. So in that case, what we do is like we would basically consider the right subarray, right? So for example, if we were searching for 5 and we were here, since 5 is more than 4, we would have simply considered the right subarray, and that's what we are doing here. So start index equals to mid plus 1. So now the start index would be 3, because index of 6 is 3. So start index would be 3, and the end index would be 5 as before. So end index won't change, but the start index will change. Okay. And then if the middle element is greater than element, so this else condition falls to that. If the middle element is greater than element, in that case we just set the end index as mid minus 1, which means like the end index, for example, if we were searching for 2, then 2 is less than 4 and 4's index is like 2, so we would have changed it to 1. So the end index of the next subarray would be 1, and the start index won't change, which means we are considering the subarray whose start index is 0 and the end index is 1. So that and the same thing keeps following till this condition is met, and whenever we find the element we return that. But let's say if we don't find, so for example in the next iteration we have 1 and 3 and we apply the same algorithm here, the middle element will come to 1 again, because this is even, like even subarray. The length of this subarray is even, and which is 2, and then we will consider the first element as the middle, and 1 is not equals to 2, so we would basically change the start index to this middle plus 1. Now the start and end index comes to 3, right? Start index and end index both are 3 in that case, and we search for 2, it's not equals to 2, then 2 is less than 3, so we change the end index to 1 minus 1, which is 0. So the end index points to 1, end index is 0 and start index is 1, which means this condition doesn't hold true, and we will simply return minus 1. So that's why this particular statement is here. Now to test again, I have done the testing over here. I assume that the list is not empty in this particular test, and I iterated through each element in the list and did a binary search and then compared the resulting index with the actual index. And I also asserted on a particular element which is not present in the list and see if it is really returning minus 1. So that's how the binary search is implemented. Next, let's look at the time complexity. Time complexity of linear search would be O of n. The reason is like we need to iterate through each element of the list, no matter if the element is present or is not present, or if there is any relation between the current element or the element. There is no it's not dependent on that. So anyways, we have to iterate through each element of the input list, and that means the time complexity is O of n, where n is the number of elements present in that list or array, and we need to traverse the whole array, and the number of comparisons is basically proportional to the number of elements in array. So that's what I have described over here. And the space complexity is O of 1, because we are not initializing any variable which is like dependent on the count of elements in that array. So we just initialize this current element per se, like we are initializing current element and idx, and they are independent of the length of this list, and they are like just two temporary variables, and they will be always the same, like we will always need to have these two initialized. So that's why it is O of 1. Complexity of binary search is O of log n, and the reason for that is, So this particular log_n is like log with base 2 of n. That's how like most of the log_n's in computer science like time complexity are about. And why is that so? Because every time you consider a middle element, you would basically discard half of the list. And how is that? If the element is greater than the middle element, you would discard the whole of left, like all the elements in the left are like discarded. And the same thing goes on the otherwise. Like let's say if the element is less than 4, then you would discard all the elements in right. And we basically keep doing that in every iteration. So we discard half of them. And that's why the overall complexity is log with base 2 of n. And we just call it as log n, which is very well understood. And the space complexity is again O of 1 because we are not initializing any other array or any other data structure whose size is like proportional to the input list. So we just initialize two temporary variables again. Three temporary variables like start, end, and middle. This three, and they will always remain the same, no matter the size of what is the size of input list and so on. So I hope you got it. And if you have any questions, just write them down in comments section. I will try to answer them or create a follow-up video around this. And yeah, happy learning.